Hey, welcome grade 11 HL chemistry students. This flip lesson, which will be a bit extended, is going to cover two topics, sigma versus pi bonding and orbital hybridization. These are special HL topics that completes the bonding unit, which is Unit 4 in the DP Chemistry curriculum. I mentioned sigma versus pi bonding. We talked about it a little bit in class, but I want to do this in a more formal way, and there is a very strong connection between these two HL topics, so I want to present them together. This is going to be a little complicated, so you're going to want to pay close attention. You're going to want to watch this or replay this at least once, maybe twice. Take notes, fill in your notes, and ask questions. Okay? All right. So let's ask this question: how do simple covalent molecules form? This is all covalent bonding. How do simple covalent molecules form? And in fact, let's ask these specific questions. Methane is CH4. We know this. But how is it possible that methane can form as one carbon atom and 4 hydrogen atoms if carbon only has 2 unpaired electrons, right? The electron configuration of carbon is what? 1s2, 2s2, 2p2, which means that, according to Hund's rule, there are 2 unpaired electrons at the 2p sublevel. Right? So how is it possible that carbon can form 4 bonds? How can carbon be tetravalent? It shouldn't be able to. Let's ask another question. In a double bond, are both bonds in a double bond the same? Are they the same? What type of orbitals are involved in the formation of ammonia, of water? These are important questions about the bonding of covalent molecules, organic molecules, which we need to understand if we're to understand their behavior and their chemistry. All right, let's take a look at each of these molecules. Let's take a look at methane. All right, how does methane form? Okay, well, carbon again is, you know this very well, the electron configuration of ground state carbon, right, a regular carbon atom in its ground state energy state is 1s2, 2s2, 2p2. And of course, because of Hund's rule, the 2 electrons at the 2p sublevel, which have 3 degenerate orbitals, x, y, and z, right, is 2px1, 2py1. The electrons go in individually before they pair up. Hund's rule. So if you take a carbon atom that looks like this, and if you take 4 hydrogen atoms that look like this, methane should be CH2, right? In fact, this 4 should be a 2. I'm sorry, this 4 should be a 2. Methane should be CH2. But methane isn't CH2. Who can tell me why? Why can't methane be CH2? You should all be able to answer that like this. You should all be able to answer that very quickly. All right? All right. So, the way methane forms and the way the orbitals come together to form methane is a process that's called orbital hybridization. It's also called LCAO, linear combination of atomic orbitals. All right. And I should say also, this is all part of the older traditional covalent bonding theory, which is called valence bond theory, right? There's no such thing as orbital hybridization in the newer bonding theory, which is molecular orbital theory. This is all part of valence bond theory. And so, what is going on here? Well, why do I have horses, donkeys, and mules? Why do I have this in a chemistry class? Okay? Well, I'll tell you why. Because a mule is not a separate species. a mule is a result of a horse and a donkey mating and forming a hybrid cross, which has some of the features of a horse and some of the features of a donkey. That's a mule. Okay, it's larger than a donkey because a horse is much larger than a donkey, but it's not as large as a horse because it's half donkey. Okay, you can see it has the donkey-like ears, but it has a longer horse-like face. It's a weird animal. It's a hybrid cross. It has properties of both. Okay, if you like biking the way I do, I love to bike, and you know what a mountain bike is, and you know what a road bike is, then this is a hybrid bicycle. Right? The tires are not as thick as a mountain bike, but they're not as thin as a road bike. Right? It's a hybrid cross between a mountain bike and a road bike. Hybrids. So back to chemistry now. No more donkeys, mules, and horses and bicycles. So in the process of sp3 hybridization, what we have is we have a carbon atom, which has this configuration. And remember, orbitals are what? They're mathematical wave functions. So what happens here is that one 2s atomic orbital mixes with, mathematically combines with, 3 2p atomic orbitals to generate 4. 1 plus 3 becomes 4 equivalent, degenerate, identical sp3 hybrid atomic orbitals. And what does this look like? Okay, well, it looks like this. 1 2s and 3 2p orbitals, they combine. These are mathematical functions. You can combine functions, right? And that's what this is all about, this LCAO, linear combination of atomic orbitals. That's exactly what's going on here. And out of this mix, we get this, right? Out of 4 atomic orbitals, we get 4 identical, degenerate sp3 orbitals that point to the vertices or corners of a tetrahedron, which also explains why carbon with 4 bonds is tetrahedral. So this is an additional way to understand the tetrahedral geometry of methane, other than the Vesper theory. And an sp3 orbital looks like this, right? It mostly looks like a p orbital. That's because 3 p orbitals are used to make it, but because a 2s orbital is also mixed in here, right? One of the lobes is actually greater than the other lobe, so it has direction. All right. So what, you say? Well, now, because you have 4 identical degenerate sp3 hybrid orbitals, and because carbon has 4 valence electrons, those 4 valence electrons all go into, one at a time, those 4 hybrid sp3 orbitals. And now, that carbon sp3 atom, hybridized sp3 atom, can now combine and make 4 bonds with 4 hydrogen atoms and 4 methane. Here's the orbital picture or structure of methane. Central carbon with 4 sp3 orbitals directed towards the corners of a tetrahedron, right? And 4 carbon-hydrogen bonds where the sp3 orbital is overlapping with the hydrogen 1s orbital, and an electron from both atoms is being shared. So this is how methane is formed. This is how ethane is formed in a very similar sense, except now we have 2 carbon atoms which hybridize to form 2 sp3 hybridized carbon atoms, right? You can see that here. 1s2, 2s2, 2p2 becomes 1s2, 2 sp3, 4. Right? 4 electrons in 4 equivalent 2 sp3 orbitals, one electron in each. And so now, in the formation of ethane, what we have is those two carbon sp3 atoms form a carbon-carbon bond using, right, one electron each, and then use the other 3 electrons in the other 3 sp3 hybrid orbitals to form the carbon-hydrogen bonds, and you have the orbital structure of ethane. Okay. Now, what about double bonds? Those are single bonds. What about ethene? What is the orbital picture of ethene, and how does it form, and what does it have to do with hybridization? Well, now we have sp2 hybridization, not sp3. So in other words, what we have here is that the 2s orbital, right, mixes with 2 of the 3 2p orbitals to form a carbon sp2 hybrid atom, which has this configuration. 1s2 doesn't change, but now we have 2 sp2, we have 3 degenerate equal 2 sp2 hybrid orbitals, each containing 1 electron, for a total of 3 electrons, with one of the 2p orbitals that was not involved in the hybridization, the 2pz orbital, with its original valence electron. So you go from carbon atoms that look like this to sp2 carbon atoms that look like this. And then what happens is each of these 2 sp2 carbon atoms forms a carbon-carbon bond with one of the sp2 hybrid orbitals and 1 electron each, right? That's one of these electrons right here. And an additional bond is formed between the 2pz orbitals, right? Illustrated here. And so what we see is that the double bond of ethene is comprised of 2 different bonds. So remember that question back here, way back here. Are both carbon-carbon bonds in a double bond the same? Well, now you know the answer is no, they're not. They are not the same. And we call this a sigma bond because the 2 orbitals are overlapping like this, end to end. End-to-end overlap is sigma. We call this a pi bond here, because the 2 pz orbitals are overlapping side to side. So sigma versus pi is simply, do the orbitals overlap end on sigma, or do they overlap side on pi? All right. Finally, we can also understand now the orbitals involved in the formation of ethine, which is a carbon-carbon triple bond. This is sp hybridization, where 2 regular carbon atoms mix the 2s orbital and only one of the 2p orbitals to give 2 degenerate sp, right, sp hybrid orbitals containing 1 electron each for a total of 2 electrons, with the 3rd and 4th valence electrons of carbon remaining in the 2py and the 2pz orbitals. And so a triple bond is actually 1 sigma bond and 2 pi bonds. It's 1 sigma bond from carbon sp, end on overlap this way. Okay, 1 electron each, right? 1 electron each. That's these electrons here. And then you have the pz orbitals, which overlap with 1 electron each to form 1 pi bond, and the py orbitals overlap with 1 electron each to form the 2nd pi bond. So a triple bond is comprised of 1 sigma bond, carbon sp, and 2 pi bonds, carbon pz, and carbon py. Okay, that is the end of this flip lesson. Is this complicated? Yes. You're going to need to watch this at least another time, and possibly 3 times. You're going to need to read in the textbook as well, and we'll practice this. Okay? But what we have done here is the following. We now have a working model for the for an understanding of how the orbitals come together to form covalent molecules, and that provides us with more information in terms of being able to understand and predict the chemistry of covalent chemical reactions, because after all, the chemical reaction involves what? The making and breaking of bonds. So we better understand how the bonds work in these molecules to be able to understand and make these predictions, right? And what we have learned is that simple atomic orbitals are not involved. Well, they're not involved. The atomic orbitals combine and form hybrid atomic orbitals, right? We have also learned that there's two ways that those orbitals can overlap. They can overlap end-on in a sigma bond, and they can overlap side-on in a pi bond. Okay? I think that's it for now. That was a somewhat longer flip lesson than I normally would like to do, but we had to cover a lot of information, right? And again, we'll practice this. We'll discuss this. You replay this several times. Read the section or sections in the textbook because this is complicated stuff. All right, that's it for now. Have a good evening. See you later.